All right, welcome back to part two. Today we're going to be continuing with the study guide where we left off. So looking at Lewis dot structure diagrams for these elements. This is all about making sure that we have the valence electrons displayed. So for carbon dioxide, we have carbon, which has 4 valence electrons. Remember, the carbon is in group 14, and therefore it has 4 valence electrons. Oxygen is in group, first of all, carbon dioxide is CO2. Oxygen is in group 16, and it has 6. So I'm going to go ahead and draw my oxygen right here with 6 valence electrons. And then since I have CO2, that means I have 2 atoms of oxygen. So I'm going to draw another atom of oxygen right over here. Now, these are bonded together. Before I say anything else, I want to say that sometimes when you have a chemical reaction and it bonds atoms together, we can have a type of reaction that we call exothermic. And so exothermic means that heat or thermal energy is leaving the substance. If you're holding a beaker of a solution or a chemical and it has a chemical reaction, if that is exothermic, it's going to make your hand hot. You're going to feel the heat coming off. The opposite of that would be endothermic. These are reactions that consume energy. So if you're holding a beaker of something and it gets very cold, it means the heat is leaving your hand. It's consuming energy or using that energy. And we'll talk more about that later on. But when we have the Lewis dot diagram for CO2, what you have to understand is that a covalent bond is where we're sharing pairs of electrons. So remember that each atom wants to have a total number of 8 valence electrons. We call that an octet. So here, what we can see, oxygen has 6, it wants to have 8, it's going to reach over and it's going to borrow the valence electrons of carbon. Over here, let me draw that in black. Over here, this oxygen atom also has 6, it wants to have 8, so it's going to reach over and borrow these atoms from carbon. So you can see that this atom now has 8, this atom now has 8. This electron and this electron will count for this atom, but it also counts for the carbon. So if we look at what we have for oxygen, we have 1, 2, 3, 4, 5, 6, and then we get to count these two, 7, 8, because they're sharing those pairs. Over here, same thing, 1, 2, 3, 4, 5, 6, 7, 8, because they're sharing those pairs. And if you look, carbon now has 8 also, because it has 1, 2, 3, 4, 5, 6, 7, 8. That is our diagram, our Lewis dot diagram for carbon. You see a double bond on this side and that side for that covalent compound. Sodium chloride is going to be a little bit easier to draw. You just need to draw chlorine. It has 7. So 1, 2, 3, 4, 5, 6, 7. When you're drawing this, make sure you put no more than 2 on each side. Okay? And then we have sodium. Sodium only has 1. I want to draw an arrow pointing over here to chlorine to show that it's getting an electron from this metal to complete its octet. The formula for sodium chloride is going to be NaCl. Alright, next we have lithium nitride. This one is a little more complex. Let me erase what I have. If you recall, lithium is in group, let's see, and then we have nitrogen. Right, so lithium is in group 1, it's a positive 1. Nitrogen is in group 15, it has 5 valence electrons, it needs 3 more, so it's a negative 3. So we crisscross these to get our formula, and we get Li3N. So to make this dot diagram, we're going to need to have 1 atom of nitrogen. I'm going to go ahead and draw it with this valence electron. So we have 1, 2, 3, 4, 5. So that's my 5 valence electrons for nitrogen. Lithium is going to have 1 valence electron each. But according to my formula, I have 3 of those atoms. So I'm going to draw it like this. Put a lithium over here with 1 valence electron. Lithium over here with 1 valence electron. Lithium over here with 1 valence electron. And I'm going to draw arrows to show that each of those atoms of lithium will donate its valence electron to nitrogen. So nitrogen will have a complete octet. When you draw the electron dot diagrams or Lewis dot diagrams for ionic bonds, it is all about the non-metal having an octet. Alright, so next we have oxygen gas, which is O2. Again, that formula is O with a subscript of 2. So remember that oxygen has 6 valence electrons. So here's 2 of those. Drawing no more than 2 on any of the 4 sides of the atom for the Lewis dot structure. In order for this atom to be satisfied, it needs to have an octet. It currently has 6. It needs 2 more. So it's going to form a double bond here. Now when it does, both of these atoms are sharing those pairs. So a line is going to represent a pair of electrons that counts for this atom and that atom. So this atom still retains ownership of that valence electron, but it shares it with the other one. And so when this happens, you have 1, 2, 3, 4, 5, 6, 7, 8. And over here, 1, 2, 3, 4, 5, 6, 7, 8. Both atoms have a complete octet, so they are both happy. Alright, so number 17 was asking you to describe the type of reactions that are occurring. Alright, so looking at synthesis reaction, synthesis is like A plus B equals AB. You could just say that 2 things are coming together. So you have element and an element coming together and forming a larger particle. The opposite of that is called decomposition. That's where something that looks like this might become that. So let's say that you had water, which is 2 hydrogens and an oxygen. If that broke apart into hydrogen and oxygen, that would be decomposition. Single displacement is going to look like this. You have AB plus C, and that's going to become CB plus A. Basically, 2 elements are going to switch places, and they're going to become something different. And when that happens, that is going to form one new chemical compound. And this often happens with ionic bonds. So this is basically a more reactive metal taking the place of a different metal. If you look at double displacement, very similar. The difference is you're going to have 2 new compounds. This would be like AB plus CD equaling AD plus CB. So looking at some examples of these. Another example of a synthesis reaction would be like if I had phosphate and I was adding oxygen gas, and what I got as a result would be this. Diphosphorus trioxide. An example of a decomposition reaction will be the opposite. If I started out with this, and then it gave me this. Okay? Again, different, just the opposite of what we had before. An example of a single displacement reaction would be this. Let's say, let me erase this actually. Let's say I had sodium fluoride. That's what they give you at the dentist's office when they clean your teeth. Plus some bromine. And then that gave me sodium bromide plus fluorine. Okay, a single displacement reaction. You can see right here that essentially bromine and fluorine are switching places. So I have one new chemical compound. Double displacement reaction. Looks a little complicated. Okay, so what we have going on right here, you see a lot of different things happening. It looks very complicated, but what's basically occurring is the calcium and the sodium are switching places, and as a result, we're going to have 2 new compounds. So that's those are some examples of those kinds of reactions. Okay. All right. Next, we're being asked to balance some equations. Okay, so it says balance the following equations and state what it is. All right. So here, let me just start from bottom and go up. First of all, this is going to be a synthesis reaction because you have two things coming together. I'm going to go ahead and make my table. We just have two elements here. Over there I have 1, over here I have 2. I have 2 oxygen, I have 5 oxygen. Alright, I need to think in terms of least common multiple. So I'm going to try to put a 2 here, try to put a 5 here, because I'm thinking about oxygen. I want to have a total of 10 on both sides. Alright, so when I restructure that and I look at what I have 10 oxygen, I have 10 oxygen, I have 4 phosphorus on this side, and I need to have 4, so I'll place 4 right there, and then my equation is complete and balanced. Looking right here, I have potassium chloride, so I'm going to have just, looks like 3 elements, so potassium, chlorine, and oxygen. So currently I have 1 on both sides for potassium, 1 on both sides for chlorine. I have 3 oxygen, and I have 2 oxygen. Thinking in terms of least common multiple, the least common multiple of 2 and 3 is 6. So I'm going to place these coefficients here, thinking about oxygen, in order to see if I can balance this equation. So let's look at what our new numbers are when I do that. Alright, so I have 2 potassium, I have 1 potassium. I have 2 chlorine, I have 1 chlorine, and then I have 6 oxygen and 6 oxygen. So my oxygen is balanced. In order to balance the equation, I'll place a 2 here, and that will change both of these elements to 2 atoms each, rendering my equation balanced. Next, I have hydrogen gas plus oxygen gas giving me H2O. So I'm going to go ahead and write my little chart over here. I have 2 of each on the reactant side. On the product side, I need to have 1 more oxygen. As you can see, I only have 1, so I need to have 2. So what I'm going to do is I'll place a 2 right here, and when I do that, it changes my numbers. So now I have 4 hydrogen, because I'm saying 2 times 2 is 4, and then 2 times 1 is 2 oxygen. So oxygen is okay. All I have to do is place a 2 right here. Now it's 2 times 2, which is 4 hydrogen, and therefore my equation is balanced. Alright, so going up to B. B has, looks like we have a sodium in a couple different places. And then over here we have some nitrogen and oxygen. So what we need to do is be very careful, because we have a situation we have sodium on the same side of the equation, and that's where it can get a little confusing. So making my little chart here, I have sodium, I have nitrogen, and oxygen. Okay, I'm going to go ahead and count what I currently have. I have 1 and 1, so I have 2 sodium, I have 1 nitrogen, I have 3 oxygen. On the other side I have 2 nitrogen, I have 1 sodium, I have 2 oxygen. And I want to think in terms of least common multiple with my oxygen. For sodium, I want to save that to last. The reason I'm saving it to last is because it appears in 2 different places. Because of that, because it can get very confusing, I want to make very sure that I save that to last, because it's easier to finish at the end. So thinking about least common multiple, I want to get a total of 6 oxygen, because the least common multiple of 2 and 3 is 6. So what I'm going to do is, I'm going to place a 3 here, and I'll place a 2 here. And then I'm going to reevaluate what I have for my number of atoms. So I have a total of 3 of those sodiums. Over here I also have 3, so that's good that worked out. I have 2 nitrogen. Over here I have 2 nitrogen, so those 2 are already balanced, that's good. Then I have 2 times 3, which is 6 oxygen, and then 3 times 2, which is also 6 oxygen. So my equation is now balanced. Looking at the last example up there, we have nitrogen plus oxygen, just 2 elements to work with. On my left side of the equation, I have 2 and 2. So remember, if you don't have a coefficient, you can envision that coefficient as being 1. I like to say that 1s are invisible. So 1 times 2 gives me those results. Next, I have 2 nitrogen, and I have 2 nitrogen and 5 oxygen. So working with 2 and 5, I can't really do anything here to make that a 5. So I need to think in terms of least common multiple. If I can make it a 10, I can work with it. So I'll place a 2 here, place a 5 there, and then I'm going to see what my new values are for these quantities of atoms. So I have 2 nitrogen still. Looks like I have 4 nitrogen now. I have 10 oxygen and 10 oxygen. So all I have to do is place a 2 here, and now 2 times 2 is 4 nitrogen. And so that's how it balances equations. Balancing equations is not fun. It does take some work. You have to kind of backtrack sometimes. You might need to use your eraser, but if you work slowly and methodically, you can find the solution. Let's create a Venn diagram comparing acids and bases.